Good afternoon, everyone. So let's start the final lectures. So I will finally speak about Markov additive processes and the fluctuation theory for these processes. And of course, the relation to self-similar processes, which has been the main topic we have been studying in this course. Okay, so yesterday we did several computations. So we did still a couple of things for stable processes. We saw some properties of exponential functionals. Okay, and well, that is so what we did during the first 3 days is somehow to motivate what can be done for Markov additive processes, or for more general self-similar processes. But of course, the techniques are much more involved, as we will see in this lecture. Okay, so well, as before, we will be considering a filter space, omega f ft, okay, and a probability family. Now this is indexed by two numbers, bar phi and x. Bar phi is in a space E and x is in R, okay? And E, I will assume, is a locally compact space with countable base. And we will assume that these are equipped of an isolated state delta, okay? So delta will be a symmetry state for the process, okay? And then I will define a Markov additive process, okay, which is, I will denote them by maps, okay, which are processes that take values in E times R, such that they have the strong Markov property still, okay, and they will be denoted by J and psi, okay. So P bar phi x is the law of the process starting at this point, okay. I will assume that these two processes die at that point, delta and infinity, okay? I will denote the lifetime as before by C, okay? And I will be assuming some regularity on J and psi as before, so I will assume that they are cat-lag processes, okay? And they are quasi-left continuous, okay? And more importantly, I will assume that both processes, the couple, J and psi, are Markov process, a strong Markov process, and J on its own, it's a Markov process, okay? But it is not necessarily the case for psi, okay? Psi on its own may not be a Markov process. It needs J to keep the Markov property. It's nice, now it is snowing. Okay, and I will be assuming that the process J and psi has this property on the increments, okay? So if you remove this J from here, okay, this is just the property that defines Lévy processes, that the increment of the process in the interval t plus s, conditionally on ft, okay, has the same law as psi s, and doesn't depend on the position of the process at time t, okay? But now I include another process J, okay? But I keep the same property for psi, so there is no dependence on the process psi at time t, but there is a dependence on J at t, okay? So that's to keep track of the position of J at time t, okay? These processes, we can think of them in the following way. So imagine you have E, which is the set minus 1, 1, okay? And you have GT, which is a Markov chain in E, okay? And then you have two processes, psi 1 and psi minus 1, okay? which are Lévy processes that are independent. Okay, so we're going to build a new process with this j and psi. Okay, so imagine j starts at 1. Okay, so we start with color red. Okay, and then j change of a state, so necessarily it goes to -1. Okay, it stays there. So let's say this one has an exponential length of parameter q1. Okay, and this one has an exponential length of parameter q minus 1. Okay, and then I switch again to +1. Okay, and then again to -1. Okay, so that's the path of j. Okay, and now on psi, I will drive the movement. Okay, so I have a Lévy process that starts at 0. Okay, and follows a dynamic determined by 1. Okay, so imagine it's a Brownian motion. Okay, and then there is an exponential time. So at that exponential time, I add a jump. Okay, and I use another process. Imagine you have now a stable subordinator, for instance. And then, again, the exponential time. I add another jump. This time is, again, negative. And I use, again, the Brownian motion. Okay. So, again, there is a jump. Okay. Some position. And now I use, again, the subordinator. So every time I switch of state space, I switch into one of these two processes. Okay? Okay, so this the new process, okay, cannot be a Markov process on its own. I mean, if I just see the movement of the particle, this cannot be a Markov process on its own because I need to know in which dynamic I started. Okay, not I started here, but from where I'm coming, in which kind of dynamic I am. Okay, it is not enough to know where I am. I need to know which dynamic I'm using. Okay, for that I need to know the state of J. Okay, that is why, in general, the dynamic of the map, the movement of the particle, okay, is not a Markov process. It could be a Markov process, yes.
What is second initial point?
This one?
Yes.
Okay, I have.
What is the
Yes. I have a jump, U1, okay, and then I have a jump here, U of -1. Okay, these are independent, independent, sorry. Okay, and then when I switch again here, I use a copy of U1 that I call U1 tilde. Okay, so let's, yeah, and then here again, I include another jump, and this is U -1 tilde. Yeah, so these are random variables. Okay, that are independent of the rest. Yeah? You're welcome. Okay. So when we have a finite state space, okay, it's very easy to well, not very easy, but it's more or less easy to understand this path. Okay? But we can have something more general because we are allowing J to be a strong Markov process in a general state space. Okay. And what is the connection of these processes with the main topic of the course, which is self-similar processes? Okay. So there is a theorem that starts from the theorem that I described in the first session, the theorem of Lamperti, that was later generalized by a student of Lamperti Q, okay, and later extended to by Chaumont, Pante, and myself, and then a more general version finally by Alili, Chaumont, Graksik, and Sack. Okay. There was before also a paper by Kuznetsov, Kyprianou, Pardo, and Watson, where they formalize in this setting the paper that is here. Okay. So here we have, as before, a self-similar Markov process. Okay. But now this one is taking values in RD. Okay. It's no longer positive. Okay. It takes values in RD. And then we define a new process, J and psi, which is the angle of x. Okay. And then the log of the radius of x. Okay? And I time change that process by tau t, and tau t is the inverse of this additive functional. So it's essentially the same as I use than the one that I use for the positive case, but I replace x by the norm of x. Okay? Well, this process happens to be this couple, okay? Is no longer a Lévy, this guy is no longer a Lévy process in general, okay? But the couple is a Markov additive process. Okay? Okay, and it will die at this state space. Okay, so when x is equal to 0, okay, I will send the process J and psi to the cemetery state. Okay? If you remember the proof of something that I did yesterday, I think, is that for when x is a positive self-similar Markov process, we show that psi t defined by log of x of bt divided by x0, okay, does not depend on x0. Okay, how did we check that? Well, we introduce a new process, so we call psi cx of t, which is the log of x bt, okay, in c times x. This guy is starting in c times x. This guy is multiplied by c times x here. Okay? And this is divided by c to the minus alpha. Yes. Okay? And then we show that this is equal in law, okay, by the self-similarity. Okay? This is log. We show that this is equal to log of x bt x, okay, and x here, isn't it? And this is the process psi x t. Okay. In doing that, by doing that, we show that that this is not depending on x here. Okay. And well, once. Let me just, was exactly that what I wrote yesterday? I just want to be sure. Yeah, I'm not, yeah, but that's okay. So this guy is starting from c times x, yeah, C to the minus alpha, yeah. Okay. And I just want to be sure. Yeah. Okay, now I can do that for any C positive. Okay? And by using C equal to 1 over x, I get rid of the dependence on the starting point, in fact. Okay? Well, now, because I'm using, when I move to RD, okay, I cannot do the same. I cannot divide by 1 over x, because x is in RD. Yeah? But I can, in fact, divide by 1 over the absolute value of x. Okay? So I will see that psi t log x bt x divided by x0 x, okay, depends on x only via the absolute value of x. The x divided by the absolute value of x. Yeah, because when I divide by 1 over x, I will get just x divided by absolute value of x. Okay? In the one-dimensional case, this is equal to 1. Okay? But in the d-dimensional is the angle of x. Okay? So this process depends on the angle. Okay? And that is why we have some things that we have that psi is depending on j. Okay? Okay. If you think on a stable process, okay, the stable process will be moving in some direction that depends on the angle, isn't it? The jumps will be depending on the angle of the process. Okay? That is why this psi, we have a dependence on the j via the jumps. Okay? Okay, so the proof of this theorem is essentially the same as the one I gave here, just noticing this, okay, that this just depends on the angle of x. Okay. Okay, so now that we have that result, and that is a very nice result, very interesting, but we saw in the previous lectures, okay, that the result was useful because we knew a lot of things for Lévy processes. And then using those properties for Lévy processes, we were able to say a lot of things on x or on random variables associated to them, like for instance the exponential function of a Lévy process. Okay? Now, the question is whether we can say something about Markov additive processes. Okay? So, what can be said about Markov additive process? Do we have the same tools as we do for Lévy processes? Okay? Can we characterize some of the maps? Like, for instance, which is the map that is behind the stable process, which is one of the things we did here. We saw roughly that we were using a fluctuation theory for the study of positive self-similar Markov processes. So it's natural to ask if there is a fluctuation theory for these Markov additive processes. Okay? And then once we have that, can we use it for something, to say something new? For instance, for stable processes, which are one of the most popular self-similar d-dimensional processes. Okay. Well, the answer to all this question is yes. We can do, and we can say a lot of things about all these processes because they still have a nice structure. Although it's more complicated, there are a lot of things that can be said. And this is something that was noticed in the 70s, Okay? In the 70s, Markov additive process appear in connection with queuing theory in particular. But they also appear in risk theory, statistical physics, financial mathematics, and more recently, via this result, in the theory of self-similar Markov processes. And there were a lot of authors that worked on this topic. Okay? So you can check the literature on the 70s, and there are a lot of results on Markov additive processes, but mainly in the case where the state space is discrete. Okay? I think it was later in the 80s, in the paper by Schindler and Caspi, okay, where they introduced, and a paper also of Maisonneuve, okay, where they introduced Markov additive processes in the study of excursions from a set. Okay? So when we study the excursion theory from one set, not from one point, okay, we have a similar theory as the one from one point, but we need to know from which point we are starting inside the set. Okay? So, for instance, there is a local time, okay, that tells us how much time we spend in a set. Okay? And the inverse of the local time still has independent increments. Okay? Both the increments will depend on the position where we are starting in the set. Okay? So we will have that the inverse local time for the excursions from a set is a Markov additive process, actually. Okay? Okay. Well, this is just the description I gave here in the blackboard. Okay. And here is a characterization of the Markov additive process when the state space is finite. Okay. So when the state space is finite, we need to describe the Markov chain, J. And we know that the Markov chain can be described via the infinitesimal generator, Q. Okay, so the rates of the process. So this is the rate at which the process J jumps from position I to position J. Okay? And then we take Uij, which is the law of the jumps that we have here. Okay, that we jump from this position to this position when we change of dynamic in J. Okay? And then the A psi J processes, which are independent Lévy processes. Okay? So each of them has a characteristic exponent, psi J. Okay? Well, if for Lévy processes we are able to characterize the dynamics via the characteristic exponent, it will be natural to do the same for Markov additive processes. Okay? And in fact, we can do that. We can, by the property of independent increments, okay, we can check that the whole law of the process is determined via this characteristic function. Okay? But we start in the position I in the dynamic J, okay? And we observe the position of the process psi at time t and J at time t. Okay? By the property of additivity of J of psi, okay, we can check easily. That's an easy exercise. That's one of the exercises I propose for today, to check that this can be written as the exponential of a matrix K times T in the coordinate ij. Okay? And the matrix K is the matrix that is diagonal, and in the diagonals are the characteristic exponent psi j. Okay? Then here are described the continuous part, okay, but also the jumps. And the jumps for the Lévy process can always be written as the integral of the exponential minus 1 times the Lévy measure. Okay? Because we are adding one jump here, then that jump can also be written like that. Okay? And then there are the rates at which we jump from one state to the other. Okay? Okay. So this characterizes, this matrix K characterizes the law of the Markov additive process. Okay? Okay, is equivalent of the infinitesimal generator for this process. And these identities, and many other identities, are described in Asmussen's book on applied probability and Qs. Okay. Tell me if I go too fast, because I'm using the slides, and usually that makes me to go too fast. Okay. In general, in a more general setting, we have that if we condition on J, okay, by the construction, psi still has independent increments, okay, and it admits a description as the one we have for a Lévy process. Namely, there is a drift, there is a continuous part. The continuous part is a Gaussian process, okay, whose covariance will depend on J. Okay? And then there are two more processes. One is a purely discontinuous process that has the same discontinuities, or that has discontinuities fixed by J. Okay? So this guy here is telling me the jumps that I do here. Okay? So it's a change of dynamics. Okay? So they are these jumps of this guy, okay, are coming from the jumps of J, and usually they are coming when we change of dynamic. Okay? And then there is another process, psi d, okay, which has independent increments, okay, but does not jump at the same time as J. Okay? So imagine in this drawing here, okay, this process has jumps that are not caused by the jumps of J. Okay? So this is YD is describing the dynamics of the particle, okay, in all the places, but where we jump when we change of dynamic. Okay? The changement in the dynamic here is coming from this YF. Okay? So think of this process as if we were adding a compound Poisson process that is independent from this one. Okay. So all these processes, the structure of all these processes depend on J. Okay? So the variance of the Gaussian process depends on J, the jump measure depends on J, and this jump measure depends also on J. Okay? In a general state space, we don't have that matrix representation, but we still have a Lévy-Khinchin formula. Because of this structure, we can use we can write a kind of Lévy-Khinchin formula for the characteristic exponent. Change slide. Okay. So here is the Lévy-Khinchin formula. So if we take the position of psi at time t conditionally on J, okay, the exponential of I lambda psi t, okay, so we'll get these three terms, okay. This one is coming from the Gaussian process, okay. This one is the drift, okay. This one is the jump of yd, okay? So the jumps that are independent of yf, and these are the jumps of j, okay, that make a jump in psi. Okay, so this is yd. Okay. So this f lambda is a characteristic function for each state, couple of states, phi0 and phi1. Yeah? So these two are continuous additive functionals of the process J. This is wrong, it should read J. Okay? And notice the form of the Lévy measure. Okay? So here we have another additive functional. Okay? So this is giving us the rate at which jumps happen in time, in S. Okay? And then this is giving us the size of the jumps. And the size of the jumps is depending on the position on J. Okay? But for each fixed J, we have a Lévy measure. Okay? Because the process is a process with independent increments. Okay? And in fact, this is a kernel. This family of measures is a family of kernels. Okay, okay, so just it's the same as the characteristic, the Lévy-Khinchin formula for Lévy processes, okay, but now we include a dependence on the environment J. And we have something else because this is coming from the jumps of J. Okay? The jumps induced into psi by J. Okay. Okay, so now can we use that, for instance, to describe the Markov additive process that is behind this table? The answer is yes, but to do that, remember we use, in the one-dimensional case, we use the compensation formula. And there is also a compensation formula for these processes. Okay, that was established by Schindler and later generalized by Benevist and Jacob. Okay? So they prove that there is an additive functional, it's the same additive functional H that appear in the Lévy-Khinchin formula, and the kernel pi, okay, such that the sum of the jumps of the process, okay, so here we're observing from which position we are moving at time S from J, okay, and from which position we are moving at time S in J to psi, sorry, in psi. Okay? So we are moving from where we are moving to where we are moving. Okay? And that can be written as the expected value of the integral between 0 and t, the rate at which jumps happen in time, okay, and the position of the jumps. Okay? This L, yeah, here we should be reading L, actually. Sorry for that. Okay. This is the measure that is appearing in the previous formula, in Lévy-Khinchin formula for psi d, yd. Okay. And this is the formula that's appearing for yf. Okay. Okay. So again, just use the classical compensation formula that you knew for Lévy processes, but add the dependence on the environment J. Okay? And there may be some rate that needs to be added. Okay. Yeah, so now, okay, how does it look like in the case of a stable process? I'm going to write it here because the next slide is not correct. In the stable case, we have a theorem that can be proved in the same way as we did in the one-dimensional case, that tells us that if we take f, a function that is going from 0 infinity times r times sd times sd, sd is the d-dimensional sphere. Okay. So remember that for Markov additive processes associated to self-similar processes, J takes values in this space. I didn't say that in the slide. Sorry for that. But because J is just the angle of the process. Okay, so it takes values in this sphere. Okay. And assume that this function f is such that in the middle term, if we have 0, we will get a 0. So we have that the expected value starting from the position theta of the sum of the s strictly positive of f of s psi s minus the jump in psi js minus js. Okay. This can be written as the integral between 0 and infinity, the integral in R, the integral, double integral in SD, and a final integral in R of a kernel v theta ds dx d phi, and then sigma 1 d phi. Sigma 1 is a uniform measure on the sphere. Sigma 1 uniform on SD times C alpha exponential yd exponential y phi minus r phi alpha plus d, and then f s x y bar phi phi, okay. And psi and j is the map associate to a rotationally invariant stable process. Okay. So we take a stable process X, so a Lévy process, okay, that has the scaling property, and we ask that this process is invariant on the rotations. Okay.
Since we saw in the integral,
Yeah.
dy is missing.
Where is the one missing? You're right. Yeah. It's in here for the, is the jump.
The dy is a Lévy measure.
Is the Lévy measure. Yeah, is the Lévy measure on R. Yeah. Yeah, these two guys are in R. And this kernel here, v theta ds dx d var phi, is ds, the probability starting from 0 theta of psi t being in dx and jt being in d var phi. This is slightly different to what I wrote in the one-dimensional case, because in the one-dimensional case, I didn't keep track of this position and of this position. Okay? But if I get rid of this position, so if I take the marginals, okay, this will integrate 1. Yeah? So if I take a function that just depends on the jump and these two, okay, then I will get something similar to what I did in the one-dimensional case. But here I keep track of the position from where I am jumping, okay, and where I'm landing, okay, because I'm working on the sphere. Okay. In fact, yeah, some of this can be verified. This can be read in a paper by Andreas Cipriano in Alea. I think it's 2018. Okay, and there you can check that the result is actually, or that the steps to reach this hold in a more general setting, okay? But to get such a clean formula, okay, we use that the process is rotational invariant, okay? But something similar will appear in the more general case. So we will have the spectral measure of the Lévy measure appearing here. Okay? Okay. Okay, so now we answer already 2 of the questions. Okay, so that the Markov additive processes have a nice structure, okay, that similar to the one of Lévy processes, that we can characterize those processes using the jump measure, the Gaussian part, the drift. Okay. Also, we saw, I mean, with this result, that we can characterize the Markov additive process that is behind a stable process, okay? At least for a rotational invariant stable process, okay? So the other question is whether there is a fluctuation theory for these processes, okay? And maybe there I should... Yeah, I'm going to switch to the Blackboard now, both Blackboards. I'm going to change to the Blackboard, sorry. Just, I will come back later maybe to this, but if you don't mind. Okay. One thing that is needed in the fluctuation theory for Lévy processes is duality. Okay. For a Lévy process, we know that if we take psi, we define psi hat to be minus psi. Okay? We say that psi hat is the dual of psi. Okay, and this is useful in several instances. For instance, to prove that psi t minus s for a fixed t, psi t plus minus s for s smaller or equal than t minus. This guy has the same law as psi s dual for s is more or equal than t. Okay. Oh, so that's maybe not what I want. I may want to write psi t minus. Has the same law. As that guy has the same law as this one. Yeah, that's this one. Okay. So when I take the path of the process, I take the position at time t. Okay, and then I see this process, I read this process backwards. Okay. I observe this process like that. Okay, this is my new axis of time. I see it from here. Okay, I read backwards. This process that I'm reading in this direction still has independent increments because this process has independent increments, okay? But what about the jumps? Look at this jump. In this direction is positive, yeah? In this direction is negative, okay? It's the only thing that changes, okay? That is why this process has the same law as this guy here. Okay? I'm just changing the sign of the process. Okay? So it's very easy to check that this happens in the case of a Lévy process. Okay? And this is important in the fluctuation theory because when we take the supremum, the infimum, sorry, at a fixed time, t, okay, then we see that this infimum, seen from here, is actually a supremum. Okay, so that relates the supremum and the infimum of the process. Okay, and that is very important in the fluctuation theory for Lévy processes. Okay. Now we are working in a more general setting. Okay, So, for instance, this kind of time reversal property, we don't know if it is true because we're working in a general Markov setting. Okay? But what do we need? We still need duality. We need a property of reversibility of Markov additive processes. Okay? In particular, when we run the Markov chain, J, in this drawing here, what do we need? I mean, we need to be able to run the Markov chain backwards. Yeah? And we need that Markov chain is reversible. Okay? So, when one needs some assumptions, one needs that there exists a probability measure, P tilde, under which J psi T still is a map, and pi a measure on E such that pi dy0 py0 0 for jt in dy1 yeah, and then psi t is in dc tilde. This is equal to pi dy1 py1 0 jt is in dy0 psi t is in dc. Okay. So I'm starting at 0 with respect to pi. I'm moving into y1 with respect to j. That is the same as starting from j1 and moving to y0. That's the reversibility property on j. Okay? But I need to keep track on the position on psi. Okay? And then we call p hat the law of j and minus psi under p tilde. Okay, this will be the dual now, and we have that then j and psi under p hat and j psi under p are dual. With respect to Lévy measure and the measure pi d theta. Okay. If we have this property, then we have this property here. Okay, we can just add another coordinate. And this happens under P. and this under S is more equal than T, and this on the P till the P hat. Okay? Or it doesn't matter. This is starting with pi. Okay? It's just that these two processes, the two processes that are there, are related via time reversal. Okay? So if I start this process here with J, and J is random with respect to pi, okay, I let it live until time t, and then I run it backwards. What I will be observing, okay, is the dual process. Okay. It's just that. Okay, so it's exactly the same process psi. It's another process because we keep track of J. Okay? So we need to find a proper measure pi and a proper process J that gives sense to this time reversal. Okay? In the general theory of Markov processes, it's known that it's not every process that we can time reverse. Okay? And when we time reverse a process, we don't get the same process. Okay? In the case where E is finite, it is enough to require that there is a measure pi or a vector such that pi multiplied by ei 0 hat exponential of minus I lambda psi t indicator jt is equal to j is equal to pi j expected value j0 exponential I lambda psi t indicator jt is equal to I. It's just like the reversibility property of the processes. Okay. That is important because if we have these kind of things, then one can prove, let's say easily, that if we take EQ that follows an exponential distribution of parameter Q that is independent on J and psi, and if we take the supremum up to that exponential time, and the infimum, then we define G EQ or paro to be the last time before the exponential time EQ where we reach a supremum in psi, and then the last time where we reach an infimum, okay? Then we have the following identity in law. So we have that, I need space, yeah. I have EQ minus G EQ sub J EQ the supremum minus EQ, and then I take G EQ here I need a, here it is the position at this time. Then this under the probability p pi 0. Okay. This is equally low to G infimum EQ J0 minus psi EQ psi infimum EQ minus G EQ infimum J G EQ infimum, and then psi EQ minus psi infimum EQ. Tac, the P pi 0. We need a drawing for this because otherwise. Well, we can actually see it here. I mean, so if this is the exponential time, okay, this is the last time we will reach this, the infimum, okay. This difference is this one here, okay. We have this one, that is this one here, okay. And then we have also this difference here. That is this one, okay, and this one here. This is psi infimum EQ. Yeah? Okay. Run it backwards in this direction. This is the supremum. Yeah? This difference here is the difference between these two guys, and then this this position here is the last. This time here is the last time I reach a supremum in this direction. Okay. It's just the justification of this generalization of the drawing. Okay. Okay. Well, now that we know that kind of things, then we can claim that there is a Wiener-Hoff factorization. And it reads as follows. Where is it? I don't want to mistake my claim. Okay, can we switch back to the, can we switch back? Can we, or that one? Oh, it's not a good idea. Because that will cover the... Okay. Oh, this is not plugged. That's the reason. Okay. This is the more general version of the Wiener-Hoff factorization. So we have that the last position where we reach an infimum, okay, this is the little GEQ that I wrote before, CQ, and the position of the infimum. So this is GQ now. Okay, I have the infimum. Okay, and then so this time here, that is the last time where I reach an infimum, okay, and the position of the infimum is independent on what we have on the right-hand side. In particular, we have that this time is independent of this time on the left, and together with this difference, the two random variables are independent of this guy. Okay. In particular, so we have that EQ and the position of the process at time EQ can be written as GQ psi EQ plus EQ minus G EQ, and then psi EQ minus psi infimum EQ. Okay, this sum is of independent random variables. Okay, and then we have more. We have that this has the same law as EQ minus G EQ plus G EQ, and then EQ. But this happens, okay, this independence is only conditionally on J GQ, JGQ minus and JGQ plus. Okay, so we need to condition on the position where we start this excursion. Okay, so we need to know in which environment we are, because remember, the process now is taking many colors. Okay, because it has several dynamics. Okay, so remember we have a process that is changing colors. This is psi now that takes several colors, okay? And so we need to know where we are starting this excursion, okay? In which color we are starting the excursion, okay? That is the dependence on this guy, okay? And when we run it backwards, we need to know where we are starting this excursion on this side, okay? That makes, it was the other way around. So in this is for the color of this excursion on the right, okay? And this is for the color of the excursion on this side, okay? It's not always the same color, because remember, we may have jumps according to J. So if J makes a jump, and that jump leads to a new supremum, then we may have different colors. Yeah? So the excursion in this direction may be starting at a different color as the one here. Okay? Okay? So we still have the Wiener-Hopf factorization, but we need to condition on this environment, on these two random variables. Should we make a break now? I think it's time. Thank you. Are there any questions before we go for a break?